A geologist and a geochemist walk into a bar. If you are hunting for mineral wealth in the 21st century, you aren't looking for easy targets. The days of finding massive, exposed ore bodies, what we often call head frame shadows, are mostly behind us. Today, the biggest prizes, the deposits that fuel our modern world, are hidden deep beneath kilometers of cover, making the exploration challenge tougher than ever. This new reality requires a fundamental shift in how we approach discovery. It demands the mandatory integration of two distinct but inseparable expertises, the structural understanding of the geologist and the analytical precision of the geochemist. We need to stop seeing the Earth only as a physical structure and start seeing it as a dynamic chemical system that leaves invisible footprints far beyond the ore itself. The discovery crisis and necessary synergy. The global mining industry is grappling with a serious problem: the declining rate of finding near-surface, high-grade deposits. Exploration has become deeper, more remote, and significantly more expensive, escalating the risk inherent in any drilling campaign. To mitigate this risk, we must convert conceptual geological possibilities into quantified, high-probability drill targets. The geologist's primary role is to establish the physical context, the structure, the rock history, and the tectonic setting that makes a region permissive for mineralization. They map, they log core, they analyze geophysical surveys, like magnetics, which often reveal magnetite associated with porphyry systems, and they define where the plumbing system, such as faults and shear zones, might exist. Essentially, they tell us where the party might have been. The geochemist, on the other hand, provides the definitive chemical evidence, the compositional proof of where metal-bearing fluids have traveled. They trace the subtle anomalies and isotopic signatures that fingerprint a mineralizing system, confirming that the party did, in fact, happen, and telling you exactly who attended. The critical success factor is the constant, two-way loop, geological interpretation guides, where samples are taken, and geochemical results refine and redefine the geological model. The art of seeing the invisible. Cryptic alteration, the most widespread and crucial footprint left by a hydrothermal system, is often not visible at all. Geologists can typically map zones of obvious alteration, but the most widespread chemical changes are too subtle to see in a hand sampler, phenomenon we call cryptic alteration. These cryptic footprints are essential for vectoring towards blind ore bodies because they can extend hundreds of meters away from the actual economic deposit, long past the point where the mineralization itself has faded out. One classic example is the sediment-hosted Elura Zn-Pb-Ag sulphide deposit in New South Wales, Australia. Here, the hydrothermal system produced detectable and systematic chemical changes in the host rocks, which are thin layers of siltstone sandstone and shale known as turbidites. The alteration was characterized by the development of iron carbonate and potassic alteration, along with the destruction of albite and the loss of chlorite in the turbidites. The most potent vector discovered was the strong depletion of sodium within the alteration system. Imagine the system acting like a giant chemical vacuum cleaner, sucking the sodium out of the surrounding rock, leaving a gaping chemical hole up to 350 meters away from the orebody, below the withering front. Simultaneously, this process enriched the rocks with pathfinder elements like zinc Zn, lead Pb, silver Ag, arsenic As, rubidium Ab, thallium Tl, and especially antimony Sb. To accurately measure these subtle chemical changes, standard whole rock analysis runs into the infamous closure problem, which makes interpretation unreliable. This is where the mathematical heroes step in, the Pearce Element Ratio and General Element Ratio Gare techniques. These methods use molar ratios formulated against a hypothesized conserved element, like titanium T, which allows geochemists to quantify element additions and losses accurately, independent of volume changes. Essentially, these ratios quantify exactly how much stuff was added or removed without getting confused by the total size of the sample. A final, crucial insight from Elura was sampling strategy. The best lithotype to sample for these vectoring purposes was the shale component of the turbidites, which provided a clearer alteration signal than the coarser siltstone-sandstone fractions. This highlights how geological understanding of rock type is mandatory even when applying purely chemical techniques. Mapping the unseen, primary halos and zonation. Beyond cryptic alteration, hydrothermal systems establish urbanized zones of chemical enrichment and depletion around the orebody, known as primary halos. These halos act like a blueprint of the mineralizing environment, providing a systematic approach to vectoring. Decades of research have established ideal models for how elements are vertically zoned within these halos, particularly in precious metals deposits like gold. These elements separate according to their volatility and the pressure-temperature conditions of their deposition. They fall into three main groups: the top or front halo, the mid-zone, and the deep tail or bottom halo. The most volatile elements, mercury Hg, arsenic As, and antimony Sb, form the front halo, nearest the surface or furthest from the source. The target elements gold O and silver Ag fall in the mid-zone, along with elements like lead Pb, zinc Zn, and copper Cu. Finally, refractory elements like molybdenum Mo, tungsten W. If you find a strong top halo signature Hg, As, Sb, but minimal gold at the level you are sampling, the message is clear: the orebody is most likely blind and waiting below you. Conversely, if you only find strong tail elements Mo, W, but no front halo elements, then you are probably sampling the roots of the system, and the valuable part of the orebody has likely been eroded away. The Los Meses project in Mexico provided a perfect confirmation of this model. Reconnaissance sampling revealed a distinctive 2-kilometer-long anomaly dominated by mercury, arsenic, antimony, and barium, all classic front halo elements. The subsequent discovery of spot highs in molybdenum and tungsten confirmed the geological suspicion that this front halo was sitting directly above a buried intrusive body, a classic setup for blind ore deposits. Modern exploration for concealed deposits now turns to even more sophisticated analytical tools to trace the invisible processes of ore formation. Two techniques stand out in advanced vectoring: stable isotope analysis and the study of indicator minerals. Stable isotopes, non-radioactive variants of elements like sulfur S, oxygen O, and hydrogen H are invaluable because they trace the origin and evolution of the mineralizing fluids themselves. Unlike simple element concentrations, which tell you what is there, stable isotopes tell you how it got there. By analyzing the ratios of these isotopes in sulphides or gangue minerals, geologists can determine whether the fluids originated from magmatic, meteoric, or metamorphic sources. In large, famous deposits like the world-class porphyry systems, sulfur isotopes detailed studies have shown that delta, for example, the core of these systems often shows strongly negative delta. This zonation helps pinpoint the high-grade zone, even deep underground. Another powerful modern technique involves porphyry indicator minerals, or PIMs. These are tough, durable minerals like zircon, apatite, rutile, and titanite that resist intense weathering and physical transportation. By analyzing the subtle, micron-scale trace element chemistry inside these minerals, a geochemical measurement, we gain a window into the source magma's chemistry, including its crystallization temperature, oxidation state, and water content, all essential geological characteristics for assessing whether a region is fertile enough to host a major deposit. This gives explorers a robust, cost-effective way to evaluate regional potential and eliminate unlikely terrain before spending huge amounts on drilling. The digital future, AI and integrated data. The ultimate challenge in modern exploration is integrating this explosion of multidisciplinary data: geophysical maps, structural logs, isotope ratios, and element concentrations into coherent 3D models that predict the location of blind ore. Traditionally, combining these multi-scale, multidimensional geoscience datasets was often subjective, relying on qualitative interpretation or cartographic overlay. This is the frontier where artificial intelligence and machine learning algorithms are proving transformative. For AI, ML to work, however, the data must be rigorously quantitative and, critically, scale consistent. This means all measurements must relate to the same physical volume of rock to ensure the spatial coupling of data is assured, a concept called integration by design. The Cloncurry Metal project in Australia is a prime example of this integrated, quantitative approach. Researchers collected 10 different analytical datasets, including density, magnetic properties, comprehensive geochemistry, mineralogy from SEM-TMA scanning, and hyperspectral data. The key was that all data were collected on tiny, standardized to centimeters, to 0.5 centimeters sample cylinders. This standardization eliminated the need to use unreliable assumptions or interpolations to mash together data collected at wildly different scales, like trying to compare a mountain range to a sand grain. By using highly predictive models, such as 3D convolutional neural networks, CNNs, explorers confused a geologist's definition of the 3D structural geometry with the Geochemist's 3D elemental halozonation. This process transforms sparse, complex data points into powerful, intuitive 3D metallogenic models capable of pinpointing drill targets hundreds of meters below cover, maximizing the value of the scarce physical data we possess. The discovery of the massive Oyu Tolgoi copper-gold deposit in Mongolia perfectly exemplifies this ultimate integration. Its discovery was not an overnight miracle, but a result of continuous, iterative refinement of the geological model based on incoming geophysical and geochemical data. The local knowledge, combined with the systematic application of geochemical mapping and structural interpretation by exploration teams like BHP Billiton, confirmed a mineralized system existed undercover, which led to deep targeting and the discovery of one of the world's largest metal mines. The future of successful exploration is entirely dependent on this two-way connection, where the geologist and geochemist continuously challenge and refine each other's hypotheses, driving us toward the next generation of massive, hidden mineral deposits. If you are interested in these subjects, please subscribe, hit the like button, leave a comment, and share this channel with your friends. Until next time, keep exploring.
Welcome to the world of geology and earth sciences with Ricardo Valls, a seasoned professional geologist bringing you over 1,500 videos of unparalleled expertise. Whether you're a budding graduate student, an early career specialist, or a seasoned professional, this channel is your gateway to a wealth of knowledge. Explore a vast array of Earth-related subjects, including geology, geochemistry, structural geology, and the application of artificial intelligence and machine learning in geosciences. Ricardo Valls not only shares his own invaluable insights, but also brings you exclusive interviews and collaborations with other prominent geologists, offering a comprehensive view of the field. Stay ahead of the curve with our latest content, covering everything from unraveling the Earth's secrets to exploring global geological phenomena. Don't miss this opportunity to enhance your knowledge and stay at the forefront of the industry. Subscribe now, hit that like button, and share this invaluable resource with your colleagues and friends. Join our growing community of over 2,000 earth science enthusiasts and professionals today. Unlock the secrets of the Earth with Ricardo Valls, your top resource for all things geology. The future of geosciences is here. Be part of it.
I think these videos are brilliant, and I'm sure you will like them too. Please like, comment, and subscribe, and don't forget to click the notification bell.